So that was about the homomorphic property and the very cool things that we can do with that. So I think next thing that we want to discuss is about the correctness of RSA. So we need to formally discuss if this algorithm is correct. Can we, if we encrypt every message, are we able to decrypt it or not? So the correctness, generally, we know that we are talking on a Zn on RSA, so which means that we should be able to deal with all the integers from 1. So let's say even 0, 1, 2, all the way to n minus 1. So when we take a M message from the Zn, we are talking about taking any of these numbers. So we want to make sure that that is correct. So talking about that, we would have some multiple cases over here. On case number 1, it is the easiest case to prove. If our message or X is from Z star n, Z star n, you remember, is the set of all integers that are co-prime to n, then proof is pretty much easy because we get this X, we know that mod n, it doesn't multiply n. It's not a it doesn't divide n. So basically, if we get any X like that is in Z star n, we raise it to the phi k times phi n plus 1, which is E times D. So let me write this one down. So we know that ED equals to is the inverse of E mod phi n. Just have all the information together. So we can say that ED equals to k, some integer k times phi n plus 1, right? So we are able to retrieve this X according to the theorem, Euler's theorem. So how about the case that, so now that we are processing every message, it could be sometimes that X is not co-prime to n, which means that X is some A times P or A times Q, so B times Q. So in those cases, we also need to be careful. So for the case number 2, so here is our thoughts. So we break the computation down into 2 pieces, mod P and mod Q. So we see that if I raise this X mod K times phi n plus 1, mod P, it is going to be 0 because X is AP. So if I take AP mod P, and if I get AP to the power K phi K times phi n plus 1 mod P, then I know that this is the multiplier of P, so this result is going to be 0, right? And then in the other hand, if we have the second case where X, if that is the case, then we also need to discuss it on mod Q. So let me also give you some other clue over here. I think we passed it very quickly. So when X is A times P, that means that the GCD of X and N is going to be X is officially A times P, and then N is P times Q. So their GCD is going to be P, right? So that is the problem over here. So, but for when X is equals to AP, for the case of mod Q, then we wouldn't have to have any issues. So let's see how so. So this is for that case, and this is for this new case. So let's continue with this case. So we are computing X to the power K times phi n plus 1 mod Q. So I can rewrite this one to be X equals to K times P minus 1 times Q minus 1 plus 1 mod Q. So this suggests that I can rearrange this to say X to the power Q minus 1, and then multiplied to k times p minus 1 mod q, right? When we are talking about mod q, we are talking about the Z group Z q, which means that the size of this group, q is a prime, so the size of ZQ is actually q minus 1, according to the Euler's theorem. So that means that this one is going to be 1, right? I'm sorry, we also have a plus 1 here. So this one is 1 times k times p minus 1. And then the plus 1, I just multiply to another x, mod q. And therefore, this whole thing here would be gone to 1, because 1 to the power of anything is 1. So the result is going to be x. So we are able to retrieve it. But we are computing x mod q. Remember, we discussed about... right.
Sorry. Where does the x came from? I lost that part, sorry.
So we said
I understand
that
the number 1, but the x...
We are encrypting some x, right? So we said that when we are encrypting some x that is in Zn, or it is Z star n. So imagine x is our message that we are encrypting. Okay, so we want to show that after encryption and decryption, we are able to retrieve the same x. So the case number 1 was when x is coprime to Z star n to n. Then that is straightforward according to the theorem, Euler's theorem. But it has happened that x is not coprime to n. Maybe x is a times p, where a times p is less than n, right? That is a valid message. That is a valid integer we can choose to encrypt and decrypt. So the story is that if we choose such a x that is a times p, n is equals to, that n equals to p times q, right? So what happened with that message? Can we retrieve that one when we encrypt it, and then when we decrypt it, do we get the same x back, or it would be different? So we break down the computation. We do that computation, encryption and decryption based on mod p, and we see that because x is a times p, the result would be 0. However, when we do that computation mod q, what we obtain is x mod q, not x mod n. So now that we have the result of some x mod p and then x mod q, then we can combine them using the Chinese number theorem to obtain that result of x mod n, right? So we can retrieve the actual n over here. So that is the catch. So no matter if you choose n that is coprime, or if you happen to choose x that is coprime to n, and that the encryption decryption, it would work well. And then if you choose an x that is somehow is not coprime to n, and in the worst case, let's say it is a times p, some integer a and then multiplied to p. So in that case, the mod p would fail, but the mod q would work. And we just do, by Chinese number theorem, we are able to show that we can combine them to actually retrieve the x mod n. It does not mean that in actual RSA algorithm, you have to check when x, the message that you want to encrypt, let's call it x, that x is a times p or a times q or not. We are just breaking down the computation here as a proof to show that even though in the worst case scenario, the message that you choose is a multiple of p or q, then if you encrypt this message and then later you decrypt it, you will be able to retrieve it. So as a part of the proof here, we are just trying to show with the Chinese number theorem that this would work. The computations are correct. Okay, all right. We don't go through the third case, which is we assume that now x is p times q, so the GCD of x and n is q. So that we have the same thing to show, the similar approach. as the case number 2. And this shows that our RSA encryption algorithm is correct, and we prove the correctness. So now that we show the correctness, it is very natural to convert RSA signature into, RSA encryption system or crypto system into the corresponding signature algorithm. And it comes actually very naturally. So the signature scheme works as follow. We first start with the key generation. I think the key generation is quite natural. We just similar to what we have at RSA crypto system, like very the same algorithm. So at the end of the algorithm, we are able to compute public key and a secret key. Now that we want to sign a message, we would do this computation. In order to sign a message, we said that we are going to use the secret key. Remember on the encryption, we use m to the power e mod n. Now that we are using signature scheme, now we use our secret key. So we do you do m to the power d mod n, and then that would be your sigma. And for the verification, we would use our public key. I'm sorry, this should be public key, and it would be 1 if and only if we raise the signature mod to the power e mod n, we'd retrieve the m. So let's see, what does that mean? If we get sigma to the power e, what we are doing is actually we are getting sigma itself. What was the sigma? Is m to the d to the power e. So this is going to be m to the power de, which is equal to m, right? So basically what we are saying here is that we just, for the case of encryption, for the case of RSA, actually, you see that crypto system and the signature scheme are quite equivalent. It's very natural. You just switch your E and D, right? In the encryption system, we use E to encrypt the message. Now we use our secret key to just, generate a signature. So instead of doing m to the e mod n, we are just doing m to the d mod n, right? So we just use them in a reverse way. And you see that this is the condition. When this algorithm verification would output 1 on this input, if this equality holds. And if somebody changed the signature or changed the m, then this equality wouldn't match. And then we would say that, we reject the signature and saying that this signature is not correct. For the case of the correctness of this algorithm, I think this is very similar to what we've discussed for the RSA, with the exception that, without no exception. This is exactly the same as the RSA crypto system. So the correctness is also there. So there is a notation and also some idea that hash then sign. How many of you have heard about this? So you should hash your message before you sign it. Have you guys heard about hash first and then sign? Or it looks like you haven't heard about it. So the story is that what we said, the signature scheme is quite natural, right? You get your message, you raise it to the power D, and then that would be your signature. And what about the case, when you have share your public key and private key already, you have your private key and you share the public key, and then you happen that you want to sign a file. So where m is larger than n, what would we do? Well, one way would be like you want to generate a new public key and then use that public key to sign. So that could work, but every time that you see a new message that is longer, then you have to regenerate your public key, right? So that is a little bit tedious, and that is not a very efficient way to deal with this scenario. So the best case scenario over here is to do hashing. So the idea is that we use a hash function. Not every hash function, it has to be cryptographic hash function. Very soon we would start to discuss what is the definition of a cryptographic hash function and what does it make it a cryptography versus every other hash function out there. So the idea is that when you apply a hash on any m, where your m could be arbitrarily long, right? So you're saying that you have an input message m, and if you look into the binary representation of this message could have any number of bits. Let's say a terabyte file, and that could be quite a lot of 0 and 1s. So the idea is that before you do encryption, before you do signature, you apply a hash function. The nice property of a hash function is that the output of the hash function is always less than n. Okay, so most of the cryptographic hash functions, for example, if you see, the output would be always fixed. Actually, it is like 160 bits, 256 bits, I don't know, 512 bits. So if you pass a gigabyte of file, a worth of file to this hash function, the output would be always like 512 bits, for example, if you use SHA-5. So this is given and is a very nice property. So I would say for all m that you choose, the hash of m, the size of the output of the hash is always less than n. And that would resolve our scenario that, sometimes you want to sign quite large message. And for that scenario, we would slightly change your signature algorithm. And whenever we have m over here on these formulas, we would replace it with the hash of m, and everything else would remain the same. So also for the verification, before you do the verification, we would have to compute hash of m, right? So that's what we are expected to compute. So this a small change over here would resolve this issue that you may encounter in practice, that message could be very long. You can never predict that. I can always sign messages of, I don't know, 10 megabyte worth. One day it would happen that you want to sign something larger. So this hash function would be quite natural and nice here. And besides that, it would also bring some security properties that are very interesting. I'm not sure if in this lecture we would be able to discuss about that, but somehow it is very important to have this hash function, and it would help us for the proof of this signature scheme. And so,
Sorry. Just a question, because I think I'm getting a bit confused. Aren't hash functions not reversible?
No. So we will get to the definitions. No, hash functions are not reversible. The hash function is a function that has quite a large domain, and then it would map it to a very small range. This is the hash function, typical hash function, okay? So, which means that by design, they are not reversible, okay? At least we are talking about cryptographic hash functions. One way that you can see in mathematics is that since your domain is large, so it would be multiple messages that they could map to the same element, right? Because the range is very small. And then when you want to map from range back to the domain, so which one is that? We don't know, right? So they naturally are not reversible. And
so having the hash of the message, like I understand we gain that it's going to be of a fixed size, but
right.
Is that like a new key, or what is, because if we cannot reverse it, why do I want it?
No, so for the signature, you don't have to reverse it. Remember that this is not the encryption decryption so that you can retrieve the message, right? For the digital signature, we just want to make sure that the message has not changed. Okay. So we just want to do that verification. And if you want to see the content of the message itself, the user has to send that message for you. Okay. So we are talking about two different scenarios, right?
Yes, thank you.
All right. Okay, so now we go through some slides, and these are very important. Now that you learn about RSA, you know that factorization is hard and all those stuff, but it does not mean that we cannot attack RSA. So there will be some scenarios that from now on we would start to discuss. And some parts, there would be some tedious proofs that I would provide for you to understand how the attack works in short. But the intention is not for you guys to find a new way to attack, but just wanted to show you that there has been some attack that they have been discovered for RSA, and then we have some patches for it. So let's just start with something more interesting before we get into the attack. I think from next slide we would get to the attacks itself. But let's talk about the speed up of the RSA. So we know that we have the RSA. It works fine now. We show the correctness. We know that we can use it for signature scheme. But is it possible that we can do a bit of speed up? We know that the major thing that we are doing on RSA is modular exponentiation, right? That is the biggest operation that we have. And if there is any speed up and any optimization that we can do there, we can save probably a lot of time or sometimes save some memory. And this is the idea here. So the first thing that we can do is having E, when you choose a E as a public key, we always raise E to the message to the power E mod n, right? So one of the optimizations that we can do is that E should have many zeros and less ones. It's very interesting. Let's see why. Suppose this is my E as a binary representation. Okay. So remember for fast, modular exponentiation algorithm, if we would start from this last bit over here, and then we said that if it is 1, then you do a squaring, and then also do a multiplication, right? And if the bit was 0, we wouldn't do multiplication, and we would just do a squaring. Squaring, some internal value y to itself, and to itself, and then we would just continue. So if you see the definition of that algorithm, it looked like that in the binary representation of E, if we have more ones, it means that we have to do more work for doing that exponentiation, modular exponentiation. And that suggests that actually if we choose our E somehow that it has less ones, then we are already doing a lot of speed ups, right? Because we are get rid of a lot of multiplications, dummy multiplications that we have there. So this should suggest that if we choose E to be 3, so binary representation of 3 is just 1, 1. So we are just doing 2 multiplying and 2 squaring. Which means that the encryption would be quite fast. Some other suggestion is that if we choose 2 to the 4 plus 1, so the binary representation of this one is 1, 0, 0, 0. So you see that you only have 1. So it means that we do 1 squaring, multiplication, and then the rest would be only a squaring and no multiplication. So this would become quite handy actually. Imagine that you have, let me give you a scenario. Suppose that you have some IoT sensors that you spread them around some field and you have them to read, the temperature of their vicinity, on some timely basis every hour. And then you want the sensors to send their readings to some server, right? To some cloud, so that you are able to pick up those values from the cloud and then average them and show, for example, what does the temperature look like in that area. So this is very interesting, but you can just have your IoT sensors to send their readings directly to the cloud, right? There are some risks. For example, the sensors would, somebody would change the temperature on the way, or some attacker would just drop their message on the way, right on the line. So you need to protect those things. So which means that maybe you need to encrypt those messages and also sign them, so that the server would make sure that this inputs, these readings or temperatures that are coming from the sensors are valid, right? It's a very natural thing to do. But we know that our sensor is running on an IoT device. It doesn't have much of computational power. So one of the ways that we can help the sensor is to choose E to have, and the binary encoding has, for example, less ones and more zeros. That would help this device. Or sometimes you just choose E to be 3, which means that it has only 1 and 1 as a binary representation. So basically, you just do one squaring and multiplication, and you're done. So you don't really push much on the sensor side. But of course, when the result get to the server, D could be quite large, and at the cloud, you don't have any problem, computing, that ciphertext to the power D for whatever the D is. So this could be something very easy and become very handy for, this IoT example that I just gave you. Another way that you can speed up the RSA is using Chinese remaining theorem that maybe you had to deal with it in your homework as well. And it's very interesting to see how you can do a speed up over here. So remember that for now we are talking about the case only for decryption, but you could also do that for the encryption as well. So remember that you need to receive some ciphertext. You have to raise it to the power D mod n to be able to retrieve the message, right? You have to do this computation for decryption. But what we can do is actually we can chop this computation. Let's say we compute y1, which is c to the d mod p. And then on the top, we can also do mod p minus 1. Because if d is greater than p minus 1, we can map it back to some numbers between 0 to p, according to the Euler theorem. So this would reduce d significantly. Also, you can do another y2, which is the same d mod now q minus 1 mod q. So you see that you are doing mod p and mod q. And once you have do this small computation, you're done with that. You can combine them using Chinese remaining theorem, and then the computation would be essentially something that look like this one if you follow the theorem. And then it's interesting that you see that this part and then this part are the same. You will find for every computation, and it means that we can pre-compute these two values, and every time that we find y1 and y2, and then we just multiply to those pre-computed values, and bingo, we have for m mod n. This also becomes very handy for scenarios where we, again, are dealing with IoT device that we unfortunately don't have enough memory to do a lot of computation mod n. This would help us to break down the computation significantly and have most of the computation to work on mod p or q. We know that p and q have half of the bits of the n. So that's quite a lot of computation saving that is happening there. And that would be very useful. All right. So it looked like that we've discussed a lot of things so far. We have RSA. We know how it works in details. We've discussed how we turn it into a digital signature. We have seen how to turn it into a digital signature, how to speed it up. Now I think it's the best time to formally discuss the security of the RSA, how much we know about it, and then is there a way that we can attack it? So those are the things that we want to clear it out now. For the case of the security of the RSA, the problem definition is basically computing the eth root of y mod n. What does that mean? It means that given some e, n, which is the public key, and some y, compute some x, or output or find x such that if you get this x to the power e mod n, you get y. So this is the basically the decrypting problem, right? So you want to find that pre-image or eth root of y mod n, and this is we try to convert RSA to this x and y equation. It is easier for us to understand in math, and then what we are saying is that there was a message that you raise it to the power e mod n and it became the ciphertext C, right? And then what we are asking you is to, given the ciphertext and a public key, output the message itself. But for the ease of what we do in mathematics, and we always use x and y, I just converted to x and y for easier understanding from here on. So this is the RSA problem, right? And then we want to use reduction and see if we can relate it to some other problem, or if in what situations we can solve it. So the first thing is the factorization of n implies breaking RSA. So that is something that we know for truth. If somebody can factor n, if given this e, n, and y, we just take this n, and we are able to factor this n to p and q, then we are done, right? So that means that given n, you can come, there is an algorithm using factorization, we can find p and q, and then using that, you can compute the phi of n, and then using that, you can find a d such that ed equals to 1 mod phi n, just like we do in key generation, right, of this algorithm. So as long as somebody, as long as, what happened to our pencil? Okay, ed, okay. As long as somebody can, as soon as somebody can factor n, then we are done. We can break the RSA. We also know that knowledge of phi n also implies factorization of n. Remember that we have showed that there is a quadratic equation, and if we just do some changing of variable, and if we happen to know phi of n, not the p and q, just phi of n, the final result, then we can solve this quadratic equation, and then with that we can output p and q, right? And then once we know p and q, we can go back to the same path and find the d and done. Okay. So this is so far what we know, but what we are trying to answer is, does breaking RSA implies factorization? What does that mean? The goal is to show that if factorization can be reduced in polynomial time to breaking RSA, to the security of the RSA security. So this is our goal. We know from one way is possible to do the other way. We have reduced the security of our RSA to the factorization. What we are trying to do is that, is it possible to show it the other way around? That if somebody can break the RSA, we can for sure use that information to do the factorization. And the good thing is that if we are able to show this reduction, so we do from one side to the other side, and then if we can show from the other side to the same side, it means that in mathematics, these two problems are equivalent. And that could be a significant proof that, RSA is indeed, solving RSA means that, factorization. And so as long as factorization is really hard, there's no way to break that one. So that one we know, but we don't know if these two problems are equivalent. So if we have that kind of proof, for now, we know that factorization is quite a tough problem. So it would give us another level of assurance that that is for sure not happening. So let's see what we are trying to do. Let me change my pen. I keep writing with blue. Maybe made your eyes a bit tired? Okay. So what we are trying to do is that we are saying that an efficient algorithm A that solves RSA problem. Okay, what does that mean? That means that given what was the RSA problem? Public key N, E, N, and Y, then he outputs some. We would basically do crypto message ciphertext, right? Such that X to the E equals to Y. So the question that we are trying to solve is that if suppose there is this algorithm, let's say suppose an efficient algorithm A solves RSA problem, then the question is that gonna imply that factorization, we can do factorization, is easy as well. So in order to formally understand that, I think now we have enough tool to discuss this formally. So we have a problem called factorization, right? And then so we want to reduce it to the RSA security, right? So the factorization, we have n. The input of the factorization is n, and we are expected to compute p and q, right? Suppose n is p times q. So in order to do this reduction, we take this n, and then we use RSA key generation, and then we pass this e and n and some y to RSA problem. And then what we would try to do, we pass this information to this algorithm A that we said we suppose we have this one that can break RSA. That A on input E, N, and Y would output X. Okay, such that, again, let me be formal. Y equals to X to the E mod N. Exactly X that we are looking for. This means that A can compute the ETH root, the ETH root, right? So the question is that suppose somebody break RSA, can we use this X somehow to compute P and Q? This is the open problem now here. So everything so far we know how to do, and we suppose that such a exists. We know that it doesn't exist, but let's just suppose it exists. Even though we suppose that it exists, and for any y, you can output the corresponding x, then there is an open problem here that we do not know how we can utilize this x so that we can compute p and q. So far, if I go back, we know that if you do factorization, we can find p and q. If you know the knowledge of yn, we can also find p and q. But somebody just solving this equation, it doesn't imply that we can use that knowledge to do to factor n. So that is the problem, open problem that is out there. Unfortunately, nobody has been able so far to prove this or disprove it, even disprove it, saying that no, there's no way that this x, knowledge of this x, would help us to find P and Q. There's no disproof. And also at the same time, there's no proof that somebody says that, and indeed, there's a way to utilize this X and compute P and Q. So that's why it remains as an open problem. And it means that breaking the RSA and factorizations problem are not equivalent. From one side to the other side, we have the proof. But from the other side, there is no proof, and it is just open problem. Well, something that is being open problem, as I said, it is like there is no proof, and then there is no disproof. So it looks like that as long as there is neither of them, we are good to go. In theory, it looks like that we don't know how we can use this, this algorithm A to get P and Q. And for the time being, nobody was able to find it. So I think as soon as somebody find this proof, it would be very interesting because we can show that breaking RSA and factorization are equivalent. You know, they have a saved, they are as difficult as each other. So that would be very interesting to have. But you know, unfortunately, we don't have that. So if some of you are interested in math, much deeper math, you're more than welcome to give it a try. All right. So I think for a couple of next slides, we are going to talk about some attacks that are possible to run against RSA. And some of them could happen for the wrong utilization, and sometimes would happen for the wrong choice of parameters for the RSA. And we will go through them, and hopefully they would give you enough idea that you should not make these mistakes and why we are going to discuss them now. So the first very same mistake is that users would start to share the same N. So you know that for key generation, you choose the P and Q, and then you compute N. P times Q is equal to N. And for that N, you should only generate one public key and private key. There is a habit that in practice can happen. Users would generate, would find two big prime numbers, and then would compute N, and would use that same N to generate different keys for different users. And they think that they are fine because they are using different E, and that means that they would have different Ds, and things should be fine. So, but we are going to show you that that is actually not true. So suppose that for this scenario, I would say a lot of times you guys would make this mistake that, for example, Alice encrypts and sends the same message M to both users. Remember that I assume that for these two users, you use the same N, but you just choose two different E and E1 and E2 to generate their corresponding public key and private keys. So this would become such a big mistake if somebody does so. Let's discuss it why. So this is the case number 1. So basically, we can do two different types of attack. So I'll discuss the case by case over here, and then you will see why this is going to be a bad choice. So if you choose for the same N, you choose two different public keys, and it happened that E1 is co-prime to E2. That means that the GCD of E1 and E2 is 1. And this implies that there is a R times E1 plus S times E2 is going to be 1, right? According to the extended Euclidean algorithm, we can find such a R and S. All right, so let's see what happens. So suppose that, so C1 is the encryption of this message under E1 mod N, and then C2 is the encryption of the same message M under to the power E2 mod N. So what happened if you raise C1 to the power R, the R that we find using extended Euclidean algorithm, and C2 to the power S, let's see what happens. So it's gonna be M1, M to the power E1 R, and then this is going to be M to the power E2 and S, right? Multiply to S. And then when you multiply these two things to each other, so you compute C1 to the power R, multiply to C2 to the power S, mod n. Let's see what happens. Then according to this computation, you get m to the power e1r times m to the power e2s mod n. And this is going to be equal to, we know that the bases are the same, so we can combine the top. We get e1r plus e2s mod n. And guess what? We know that this equation is going to be 1. So we get m. Very interesting, right? So if Alice used the same n and just generate 2 different public keys for 2 different users and encrypt the same message and send them to those 2 different users under their different public keys, if we just get these 2 pieces of ciphertext and we compute this thing based on E1 and E2, these are available in public. We can just use extended Euclidean algorithm to compute it. C1 and C2 are also publicly available. So if we just raise them to the power R and S and we multiply them together, we can actually recover M. So this is such a big mistake if you use the same N to generate different public keys for your users, right? So the lesson that we should learn from here is that if you have, let's say, many servers, and let's say those all servers would do the same computation, and it is going to be a very bad idea for you to use the same, find a P and Q and compute N, and then use the same N to, to compute different public keys for your server. And now this attack, you see that if 2 users are sending the same encrypted message to those servers, then somebody on the line would be able to do this small computation and recover the M. And we should avoid this by all. All right. So this is the case number 1. And also we have another case for this attack that I think after the break, we are going to show you that actually one user can recover the other user's private key. So we will get back to that after our break time. So let's take some break time now.